Inductors come in many shapes and sizes. Conductive windings surround an iron-based core to provide temporary energy storage and to regulate the current flowing through a circuit. To make an inductor, they use plenty of flame-resistant insulating material. They cut sheets of it to the desired dimensions. An operator programs this automatic shear to cut the electrical insulation into long strips. The hydraulically driven blade makes clean, straight cuts. These strips will be used to insulate the inductor core and coils. A worker folds a rectangular piece of insulation around an aluminum form to start the inductor coil. She tapes the ends together. She pulls a strip of copper foil to the insulation. She's pre-soldered a terminal to the end of the foil, and she tapes the terminal to the insulating material. She begins to wind the copper foil around the insulating material and stops. She places one of the long insulating strips under the copper foil and resumes winding. This prevents short circuits. She clamps the copper windings tightly together and tucks an extra piece of the insulation under the copper. She hammers the copper to flatten any kinks. She solders a second terminal to this end of the copper foil windings. These terminals will be used to connect the inductor to the electrical circuit. She holds the terminal in place with a metal dowel and the soldering iron until the solder solidifies. She then cuts the copper strip along the edge of the terminal. She applies fiberglass tape to the soldered terminal joint. She removes the clamp and adds more tape to keep the terminal in place. She then winds fiberglass tape around the outside of the inductor coil. This outer wrap will prevent shocks to anyone who might touch the inductor when it's part of an electrical circuit. Using a tough nylon block to absorb the impact, she hammers the inductor coil to make it more rectangular. She removes the coil from the winding machine. Next up is this hard polyester-infused fiberglass. They'll use it to insulate the core and fill the gaps. With the hydraulic shear, a worker cuts the fiberglass into strips that will fit in the core. A worker clamps two of the insulated copper windings side by side. She inserts a C-shaped iron core in one end of the copper windings and flips the inductor assembly over. She connects the protruding terminals with a tinned copper jumper. She inserts insulating spacers into both cavities. These fiberglass spacers will fill the gap between the two iron Cs. She installs the second half of the iron core. When alternating current is applied to the copper windings, it will create a magnetic field in this core, and this is how the energy will be stored. She tucks a couple of fiberglass insulating spacers between the iron Cs and the coils. She drives them deeper into the inductor. She loops a stainless steel band around the iron core and pulls it tight with a pneumatic tensioning tool. She solders the ends of the band to secure it. They immerse the inductor in a vat of varnish under vacuum pressure. The varnish completely seals the inductor against dirt and moisture. To confirm that the inductor meets specifications, a technician applies 2,000 volts of energy between the core and the windings for 1 second. The instrument detects any problems with the insulation. It's one of several tests conducted. If the inductor passes them all, it's ready for the electrical circuit.